So some high-level ideas or some various classes for performing RL, and during the course we'll dive deeper into each one of these classes and break it down to also to subclasses. But some high-level ideas here would be model-based reinforcement learning approaches. In model-based approaches, we try to learn the transition probabilities, which previously I told you we don't assume to know those, but we assume that those actually exist and are stationary. So in model-based approach, we will, or these approaches try to learn these probabilities and also try to learn the reward function. If it's not, so in some cases it can be provided explicitly, but in most cases it is implicit. So model-based approaches will try to learn the full model, the reward function and the transition probabilities, and based on those distributions to solve, to optimize the policy. Either it can be done online, offline, or in some mixtures of online and offline algorithms. Next, we have model 3. Actually, most of the solutions that we will see will concentrate and that you will implement will concentrate on model 3 reinforcement learning, where we learn a policy without knowing or without learning the model, the transition function and the reward function. So by the way, when I say we don't learn the reward function, I don't mean that we don't observe the rewards, right? So we always assume to be able to observe the rewards for each state or transition that we encounter in the environment, even if we don't know the reward function. That's definitely a possibility. So for model 3 reinforcement learning, we look at two main approaches, either value-based reinforcement learning, where we learn a numerical value for each state or action state pair, representing the future expected utility to be gained. So in this setting, main RL approaches, reinforcement learning approaches that we're going to cover during this course at the highest, I'm going to discuss those at the highest level, and of course these general classes can be further broken down into subclasses. So we will look at model-based approaches. These approaches try to learn the model, they try to learn the transition probabilities and the reward function, and then optimize the policy either offline or online, or in most cases in some combination of online and offline learning. Then we will also discuss model 3 approaches. Actually, mostly we're going to discuss model 3 approaches, and you're going to implement most of the approaches that you're going to implement. I think all of the approaches, maybe, yeah, I think all of the approaches that you're going to implement are model 3. Where you learn a policy without knowing or without learning the model. So this can be further broken down into value-based reinforcement learning, where we learn some numerical representation for each state or each action state pair, and that will represent the future expected utility to be gained from that state or state action pair. And we'll also look at policy-based reinforcement learning, where we learn actions that improve on a given policy, and then we improve the policy and we repeat this process until we converge. So these approaches can be further classified into either act or critique approaches. Sorry, these approaches where we both learn a value for each state or action state pair, representing the future expected utility, as in value-based approaches, but we use the learned values in order to decide how to change a policy, a given policy, right? So we improve the policy and then we repeat this process until convergence. So this is kind of a combination of the value-based approach and the policy-based approach. Okay, we combine both of them. These are mostly state-of-the-art approaches. These days they follow an actor critique architecture. And eventually we're going to discuss deep reinforcement learning, where we use deep neural networks in order to approximate either our value function, the state value, or the state action pair value. So state value is we use the capital V to represent that function, a function that tries to learn the state value. If it's an approximation function, we approximate these values. We use a hat over the v, right? So the hat will be used to represent approximation. So this is a mapping from states to some value, or learning an action approximation, which is represented usually with a q. Again, with a hat means that we approximate that value, which maps state and actions, pairs of state and actions into some value. In deep reinforcement learning, we use deep neural networks in order to approximate these, and either approximate also a policy, or sometimes in actor critic architecture we actually approximate both, but we also approximate a policy, which is, as before, a mapping from state to actions, or, I didn't include it here, but we'll see it later, or in many cases a mapping from state to a distribution over the action space. So, and you can also look at it as a mapping between a state and action pair to a probability.